can't win. You definitely can't. But, well. All right. Well, I guess it's about that time. And it's not too early, but hey. Homework should be turned in today. I think I've gotten at least most of the submissions from the online students, so you can go ahead and turn those in sometime before you leave. I took the quizzes back to my office and then I set them on the desk and proceeded to ignore them. And will continue to ignore them at least until the end of class. And I will grade them this afternoon and get them back to you tomorrow. My excuse is that I want to wait for all of the online students to complete it so I can grade them all in one big lump. And they are only now officially closed to taking the quiz. So I don't know if that's a good excuse, but that's what I have, and that's why I'm sticking to it. So looks like the exam will go ahead and be on Monday from 6 to 7:30. I'm going to go ahead and today reserve the room, and I will let you know when that's going to exactly be. So that means that I'll probably go ahead and do the exam review tomorrow at the last half of class so that you have an opportunity over the weekend to decide what you're going to study and ask any questions that you have. And then we'll just go ahead and start on some new material come Monday. But what I would, yeah?
The exam this Monday?
Yeah.
Oh, okay.
Yeah. I know, what is that, like 4 or 5 days, something like that. But basically, like I mentioned, the exam will cover there'll probably be one question they ask you to do a Thevenin analysis, Thevenin equivalent for something that contains a dependent source in it. There will be probably one first order circuit, one second order circuit, and then some sort of AC analysis, and that will probably kind of be the extent of what you'll see on the exam. Maybe a couple other little questions where I just ask you to determine the Thevenin resistance, or determine the time constant tau for a given first order circuit or something like that. But that's probably about the extent of where we'll go with it. That's probably about it. Then there might be one question where you're asked to determine the voltage across the capacitor or something like that, just to see the capacitor by itself or something like that. But the homework questions generally will give you a pretty good idea of what I think is important. So, solutions for homework 4. I started them earlier today, and I will get them finished up and posted today so that you can use those to study. And I'll post at least a few suggested problems from this AC analysis chapter. Yeah?
I guess especially for like the second order stuff, will there be a few equations
Yes.
included?
Yeah. There will be an equation sheet attached to the back of the exam that will have the form of all of the responses. The equations that you use to solve for the constants, B1, B2, K1, and K2, so on. The equations for the first order circuits as well, just, K1 plus K2 e to the negative t over tau, and how to solve for K1 and K2. The only thing that I'm going to ask you guys to remember essentially for that is the relationship between omega naught and alpha, whether it's which form of it's going to take, so whether it's going to be overdamped, underdamped, or critically damped. So. But we'll look at that stuff again in a little bit more detail again tomorrow, starting at the second half of class or so. Otherwise, I think, are there any questions? Because if not, I'm just going to go ahead and get started. Most of the material for lecture 7. I think it's chapter 8 in the textbook. All right. So let's see what we did yesterday. We started looking at phasor relationships for our normal circuit components, the resistors, capacitors, and inductors. And then we looked at these concepts of, or the concept of impedance. So when we looked at resistors, we found that as a function of time, voltage equals resistance times current. That doesn't change when we move into the phasor domain, so it's still just voltage equals phasor, or the resistance times the current. There's no complex portion, which means that the voltage and current are in phase. So if you have a voltage of that has a phase angle of 30 degrees, the current's going to have a phase angle of 30 degrees, and so on. And we did a quick example with that one. We found the same kind of relationship for an inductor, except now we do have a complex component to it, and there's also a frequency component to it, and that has two major implications. The first is that the voltage leads the current by 90 degrees. So I think this is right, that if your current has a phase angle of 60 degrees, then the voltage should be at, I think, negative 30 degrees. But the response is also frequency dependent, which means the larger the frequency gets, the larger the voltage gets, even if you don't change anything else. So if you have 2 amps of current for a fixed inductor, but you change it from 60 to 120 hertz, that's going to double the voltage as well without changing any of the other components. But also practically speaking, if we think about the radian frequency being 0, or in other words, the having a DC current or DC circuit in general, you can see how very quickly the voltage goes to 0, which we're used to. An inductor short circuits under steady state DC conditions. And we did a quick example. Also, with the capacitors, this time things got switched around just a little bit. The current is given as j omega times the capacitance times the phasor voltage. Again, we're looking at voltage and current being 90 degrees out of phase. This time the current leads the voltage instead. And again, we're also frequency dependent, but it's definitely important to look at, which side of the equation each of these components is on, the voltage and the current. But you also see that if you pop in 0 as the frequency, you see that the current goes to 0, and also that's familiar. Capacitors act as short circuits, or as open circuits during DC conditions. So, and we did another quick example of that. And then we introduced this concept of impedance, and we started talking briefly about admittance. And this is the full AC equivalent of what's going on with resistance. It's the same kind of thing, and like I said, it's kind of the great equalizer. Resistors exhibit impedance, and as do inductors and capacitors. And the relationship between voltage and current is the impedance in general. But we're looking at those as being complex numbers, but for whatever reason, despite the fact that we will almost always represent, express the voltage and the current as a phasor, we will almost always express an impedance in rectangular form. And I think the idea there is to make very clear the difference between the real and the reactive parts of the impedance. So calculating impedance for the various circuit elements is very straightforward. For a resistance, it's simply the resistance is the impedance. It's the same thing. For an inductor, you multiply J times omega times L, and that will give you the impedance for that element. And then the way that I was always taught impedance for a capacitor was negative J upon omega C, or negative J over omega C will give you the impedance for the capacitor. Yeah, for a capacitor. And the general form of the impedance is Z equals R plus JX, where R is the real or the resistive part, and X is the reactive part of the impedance. So we looked at combining things. Impedances combine like resistance. So if you have them in series, they just add up. If you have them in parallel, they add up reciprocally, just like you're used to. So there's nothing particularly unique there. But certainly, if you start combining a bunch of complex resistances, the math is going to get ugly pretty quickly. And so we did at least one example, and I've got at least one more good example to take a look at. Yeah. So let's do that. So circuits. And perhaps yesterday we looked at our first proper AC circuits, and perhaps this is really our first proper AC circuit to do some analysis on. But here's a 50 microfarad capacitor, a 20 ohm resistor, and a 40 millihenry inductor. This voltage source is V of t, and just for sake of room, the sinusoidal voltage that it creates is 120 times the sine of 377t plus 60 degrees volts. Probably the first thing to do is to get rid of the silly sine stuff and get it as a cosine instead. And just want to verify my math on this one. You subtract 90 degrees to get that as the... Oh, I always forget this. Yeah, subtract 90 degrees to get it into the cosine form, which will make our lives a little bit easier. So that's 120 times the cosine 377t minus 30 degrees volts. And that makes it a little nicer to put it into the phasor form. So the phasor form of that voltage is just 120 at an angle of negative 30 degrees. So the first step is to take and find out what are the impedances of all of these circuit elements. So what is the impedance on the resistor, impedance on the inductor, and the impedance on the capacitor. Now with the resistor, again, it's really easy. It's just the resistance. On the inductor, it's J times omega times L, which is J times 377 times 40 millihenries. And that is 377 times 40, 15.08 times J. And the capacitance is negative J upon omega C. And so, so that's negative J over 377 times 50 microfarads. So 377 times 50 micros. Flip that, and you get 53.05. Negative J, 53.05 ohms. So those are our impedances. The whole thing that we would like to be able to find here is a current I of t. So perhaps the easiest thing to do now that we have some impedances is to take and combine those in parallel. We'll combine these two in series, combine the whole thing in parallel, and divide the voltage by it to find out what the current's going to be. So at least that's at least one simple way of doing it. We could certainly do a nodal analysis or something, but it's kind of getting the cart before the horse. So let's combine the resistances. Combining the resistor and combining the impedances. Combining the resistor and the inductor is not a big deal. Those are just, one's wholly real, the other one's wholly reactive. So the series impedance is going to be 20 plus J 15.08 ohms. And then the overall impedance, or equivalent impedance, will be 1 over negative J53.05 plus 1 over 20 plus J15.08 to the negative 1 power, or, flip it. And here is where it's important to be really careful about your math. So we say 1 over 0 negative 53.05 plus 1 over 20 15.08, and flip that. Yeah, good. And so when you do that, you should get something in the neighborhood of about 30.56 plus J 4.97 ohms. At least, again, the rounding could get you something slightly different, and calculator precision is going to make things just maybe a little different, but that's approximately where you should be at. Ohm's law tells us that if we want to know the phasor current, we can divide the phasor voltage by the overall impedance. And so that's 120 at an angle of negative 30 degrees. And divide that by 30.56 plus J 4.97. 120. 30.56, 4.97. Should get you, well, let's get that into a form that we like better. Put it in a polar form. So that's something in the neighborhood of, I don't know, 3.88-ish at an angle of negative 39.24 degrees, amps. Again, rounding might make your numbers just slightly different from mine. But that's as a phasor. We would like to find it as a time function, and so we can pretty quickly take and say, all right, well, I of t, we're working at the same frequency, so it's 3.88 times the cosine of 377t minus 39.24 degrees amps. So I think the the hardest part with this is going to just be bookkeeping on the complex numbers and making sure that as you start punching that stuff into your calculator that you don't mess it up somehow. But that would be, when I get into this material for the first time, after being away from it for a while, the hardest part is just keeping track of all of the complex numbers. The rest of it is stuff that should be pretty familiar. I mean, if I gave you just 3 resistors and asked you what is the current that's flowing through there, I think that you guys could do it, one way or another. The circuit doesn't behave any different. We just turn these into impedances and use slightly more complex ways of expressing the currents and stuff. But looking at the slides again just for a little bit, we define the concept of admittance, which is more or less the same thing as conductance, because it is the ratio of current to voltage, or it's 1 over the impedance. Just like I have no use for conductance on a daily basis, I don't have any use for admittance personally. I don't find it to be a useful concept in any way. But it's there. It's because it is an inverse, or it's 1 over it's 1 over an ohm. That means it's measured in Siemens, and it's also complex. It's generally expressed in rectangular form, and the general form is Y, which is what we assign the admittance to, equals G plus JB, where G is the conductance and B is the susceptance. I think they were running out of words that indicated that current would indeed flow. But it's there. You've heard it. I've done my duty, and now I will promptly never talk about it again. This is another thing that I don't really particularly care for a lot, and so I will I'm going to kind of breeze over it because it's not, you guys have talked about phasor diagrams a little bit in DSP, and I don't really like them. I am not a visual person, and they don't help me in any way, so I'm not going to talk about it too much, but it can be helpful to talk about the way that a circuit relationship will hold as the frequency starts to change, and a phasor diagram tells you what that looks like. So just for what it's worth, as a simple example of this, we can have current source, resistor, inductor, capacitor with equivalent, and this gives off some phasor current I sub s. We have a resistance, we have an impedance of j omega L and an impedance of j over omega C. And if we wanted to look at, for example, what is the relationship to the voltage and the current, if the voltage, for instance, were to just go straight out along the x-axis, the current for the capacitor would be kind of cruising up that way. The current for the inductor would be down this way, and the current for the resistor would be in phase with the with the voltage. And obviously you can start combining these things to find out, well, if we combine these two, what is the relationship, between the phasor voltage and current and so on. My executive decision is that I still don't like this stuff, so I won't ever ask you to draw a phasor diagram because I just don't even find them useful. But you can look in the book if you really think they're useful. I just don't, so I'm going to skip it. More interesting stuff. Analyzing AC circuits. Anything that we've learned in the previous chapters is perfectly fair game to use to analyze AC circuits, with the exception of transient analysis. Transient analysis is all about the fact that we're in DC conditions, and once you get rid of the DC conditions, you automatically don't have anything more interesting to talk about for transient analysis. But Ohm's law holds, KCL and KVL holds. You can do current and voltage division. You can do nodal analysis, mesh analysis, superposition. You can create Thevenin and Norton equivalents. All of those things are perfectly fine, and we can do lots of examples going through those things, and that's what we'll do. Now, again, the hard part with this is just dealing with all of the complex numbers, and that's kind of the only bad part about doing it. And so what we'll do is we'll cruise through, and we've got a couple examples. I'll do one, I'll ask you to do one, and then we've got one circuit that we'll look at 4 different ways and just show you that you get the same answer and so on. So, AC circuit, voltage source, resistor, inductor, resistor, capacitor. This voltage is 24 at an angle of 60 degrees. This is 4 ohms. This is J6 ohms. This is 8 ohms. This is negative J4 ohms. And we want to find all of these marked voltages and currents based on what we have. So we're going to call this one V1. This will be I2, right? Yeah, I2. And here is I1. So, so we can do this in the nice simple way, very similar to what we did before, which is to kind of collapse the circuit down at least a little bit, figure out what the original current is, I1, and then start doing some like voltage division, current division kinds of things. So let's go ahead and do that. The equivalent impedance here between these two is just going to be 8 minus J4. And that will be in parallel with the J6 inductor there. So we can redraw the circuits, and we'll simplify this down to the box version, where this is still going to be 4 ohms, and this is going to be some equivalent impedance, CEQ, and this is still the 24 at an angle of 60 degrees volts. So 1 over that equivalent impedance equals 1 over 8 minus J4 plus 1 over J6. And 1 over 8 minus J4 plus 1 over J6. Flip that, and you get, something in the neighborhood of about 4.24, well, the equivalent impedance equals 4.24 plus J 4.94 in that neighborhood. Again, rounding might change your numbers slightly. So what's the voltage across this equivalent impedance? Well, we can do a simple voltage divider. So the voltage across, just call it Z. Well, actually, let's call it V1, because it is the same voltage V1 that's across this inductor as well as this equivalent impedance. So that's going to be some fraction of the 24 at 60 degree volt coming out of the source. We put our equivalent impedance on the top, that's the one we're interested in, plus J 4.94 over, and just simplifying things quickly, you have 8.24 plus J 4.94. That's the combination of the 4 ohms of real resistance and the equivalent impedance there. So punching those numbers in, 4.24 plus J 4.94 divided by 8.24, 4.94J. Multiply that by 24 at an angle of 60 degrees. Put that into polar form. And should get something, yeah, good, in the neighborhood of about 16.26 at an angle of 78.42 degrees. Give or take. So that's voltage V1. If we know what the voltage V1 is, and we can figure out what the current I1 is, or let's see. Yeah, we could go ahead and if we know what the voltage is across this equivalence impedance, divide it by that, we can find out what the current is that was running through there. So then that should be I1, which is going to be 16.26 at an angle of 78.42 divided by 4.24 plus J 4.94. Oh, 78.42 divided by 4.24, 4.94. Let's get back up here and do this right. 16.26, an angle 74.2. Yeah, that looks good. And put that as a, yeah. So life is still pretty good here. We've got 2.49, 2.5, whatever, at an angle of about 29.06 degrees. So that's a couple of the things we wanted to find out, at least what is the current that's going through. So we have I1 and we have V1. The last two things we wanted to solve for real quickly were what is I3 and what is V2. So we can say, well, the voltage V1 is still across that J6 ohm inductor, and that happened to be 16.26 at an angle of 78.42 degrees, again. And so the current I2 will just be that voltage, V1, divided by J6 ohms. So this is, all of this, none of the work should look particularly odd here. It's just, these are the same things you do if this was a DC circuit. You're just dealing with complex numbers when you're actually running the numbers. So we take that voltage, 16.26, at an angle of 78.42, divided by J6 ohms, and you get 2.71 at an angle of negative 11.58 degrees, or thereabouts. KCL says that the current running in, so I1, equals the current running out, which would be I2 and I3. We would like to know what I3 is. It's the only one that we haven't solved for already. So we can say that I1 minus I2 equals I3. I1, if we look back on the previous page, was 2.49 at an angle of 29.06. I2 we just solved for as 2.71 at an angle of negative 11.58 degrees. And that should give us the value for I3. Minus 2.71, an angle of negative 11.58. To rectangular polar form. Yeah. Now this one intuitively looks a little weird, right? I just subtracted something that this looks like it should have a negative answer, doesn't it? To me it does. When I look at that I say, well, this is a larger magnitude, and so, but because of the difference in the phase angles, it actually works out to be in, as a phasor, 1.82-ish at an angle of 105.26 degrees. Which seems a little odd to me, I mean, to be on a personal level. But, hey, it works. The last thing that we wanted to figure out was what was the voltage V2, which was the voltage across the negative J4 ohm capacitor. We know what the current is that's running through it, I3, so we multiply I3 times negative J4. So that'll be 1.82, an angle of 5.26 times negative J4. 1.82 at an angle of 105.26 times negative J4. Yeah. The numbers are diverging a little bit more because of my various rounding, but about 7.28 at an angle of 15.26 degrees. So, and again, when I look back at my notes, the phase angles are slightly different, but only on the order of the decimal points. And again, it all has to do with the way that I've been rounding as I go through the process. So, hopefully, as you watched me go through that work, you didn't see anything particularly weird. Everything that I did is something that we learned. This is all like chapter 2 kind of material. Looking at how we can combine resistors in series and in parallel, figure out, do a voltage divider, maybe do a current divider kind of thing, use Ohm's law to figure out what's going on with a little bit of KCL mixed in there. It's just we're working with complex numbers instead of, just real numbers. So why don't you guys try one real quick? This one is not is pretty straightforward. And all we want to have you do, and you can do this in any way that you want, but I guess kind of the intention is for you to do it maybe the hard way. We have this circuit. The authors were not particularly were not particularly creative when they decided on their impedances, so everything is either J2 or negative J2. And what they want you to do is, if we know that V0 equals 8 at an angle of 45 degrees volts, so if V0 is that, what is the source voltage? So take, let's say, 4-ish minutes to work on that. If people get done before that, we'll come back together. But give that one a crack. It shouldn't be too hard. as you guys finish up your work, I will start kind of working through my version of the solution. So if we know what V0 is, probably the first step is to figure out what is the current that's running through that 2 ohm resistor. So let's just call this, to be consistent with my notes, I'm going to call this current I3 that's flowing through both the capacitor as well as that 2 ohm resistor. So that current I3 will be equal to V0 divided by the 2 ohms of resistance. At an angle of 45 divided by 2 equals 4 at an angle of 45 degrees. And that's the current that's running through there. So the entire voltage, and again to be consistent with my notes, we'll call that V1, that's going to be across both the capacitor and the resistor as well as across the inductor, because they are in parallel, will be, V1 will equal the 4 at an angle of 45 times negative J2, that's the voltage across the capacitor, plus the voltage V0, which is 8 at an angle of 45 degrees. And when you work that out, you should get 11.314-ish at an angle of 0 degrees volts. So again, to be consistent with my notes, then we can find out what I2 is. I2 will be the voltage 11.314 at an angle of 0 degrees volts divided by the resistance, or divided by the impedance, which is J2. When you calculate that out, you should get 5.66 at an angle of negative 90 degrees. Amps. So then I1 would equal the sum of I2 and I3. KCL tells us that. I2 we solve for as 5.66 at an angle of negative 90 degrees. I3 we solve for as 4 at an angle of 45 degrees. And the sum of those two is, I'm going to verify this one because my math is a little shaky here. Negative 90 plus 4 at an angle of 45 so you get you get 4 at an angle of negative 45 degrees amps. So now we could do a KCL kind of, or a KVL kind of thing going around the loop. So the negative Vs equals the voltage across the 2 ohm resistor plus V1. Let's see, let's do this right. Negative Vs plus V2 ohm plus V1 equals 0, or in other words, the voltage across the source is going to be equal to the voltage across the 2 ohm resistor plus what we marked as V1 on the previous circuit. We know what V1 is. We solved for that already, and that is that 11.314 at an angle of 0 degrees. But we need to know what the voltage across the 2 ohm resistor is, and that's going to be 2 times the current running through it, I1. So that's 2 times the current we solved for is I1 is 4 at an angle of negative 45 degrees plus 11.314 at an angle of 0 degrees. Should be just 8 at an angle of, well, let's make sure it's right. 2 times 4 at an angle of negative 45. Yeah, that's just 8 at an angle of negative 45 plus 11.314 at an angle of 0 degrees. And put that all together, and you should get that the The voltage across the source is 17.89 at an angle of negative 18.43 degrees. So nothing too scary there, I don't think. Just keeping the math together. That's the hard thing. Okay. This is my least favorite part of this lecture. What we're going to do is we're going to take a look at one circuit. Actually, we're going to look at two circuits, and I'm going to do them 4 times to show you that you should be able to get the same answer with all of these different analysis techniques, and that all of the techniques that we learned in in the previous classes all can apply right back to AC circuit analysis. So here's the circuit that we are going to get somewhat sick of taking a look at. Resistor, inductor, current source, voltage source, very inconveniently located. Resistor, capacitor. Capacitor is negative J1 ohms. 1 ohm resistor, 1 ohm resistor. The current that we want to find at the end of everything is that current I0 that's flowing through that 1 ohm resistor there. The magnitude of this is 6 at an angle of 0 degrees. This is 2 at an angle of 0 degrees amps. This is a J1 ohm inductor, and this is a 1 ohm resistor. So, let's start out with nodal analysis, which is going to be kind of crummy because, well, that means that we need a supernode. And the way we are going to simplify things a little bit here is that we can obviously combine these, especially since we're not looking to solve for any of the particular voltages across any of these individual elements. We can just combine these, the inductor and the resistor, the capacitor and the resistor. We can just combine those in series and think about them as just being 1 plus J1 and 1 minus J1 and not worry about writing like an extra 2 node equations. But this requires a supernode, so we will deal with that. So in this case, V2 minus V1 equals 6 at an angle of 0 degrees. And start writing node equations. Awesome. All right, so we have V1, which is connected to the reference node with over 1 plus J1. We have 2 amps of current running in, so that's going to be minus 2 at an angle of 0 degrees. So that's it for the node V1. V2 is connected to the reference node with a 1 ohm resistor, so that's, I mean, we can write it in as V2 over 1, but I mean, eventually that will very clearly disappear. And then we have V2 over 1 minus J1 equals 0. So the one that we would probably rather see, we would probably rather have, is going to be to solve everything in terms of V2, because the ratio of V2 over 1 is going to give us our current I0 anyways. So let's rewrite this equation so that we can replace all the occurrences of V1 with a V2. So that's going to be V1 equals, that's putting that onto the other side, equals V2 minus 6 at an angle of 0. So pop that in. So we have V2 minus 6 at an angle of 0 over 1 plus J1. We'll put that over on the other side here in a minute. Plus V2 plus V2 over 1 minus J1 equals 2 at an angle of 0. try to simplify this a little bit more. So this is V2 over 1 plus J1 minus 6 at an angle of 0 over 1 plus J1 plus V2 plus V2 over 1 minus J1 equals 2 at an angle of 0. So first thing I want to do is try to deal with this constant term, 6 at an angle of 0 divided by 1 plus J1. It's going to give us I think for just a minute here, I'm going to break with convention because we can get perhaps a slightly more accurate representation. Say this is V2 over 1 plus J1 minus 3 minus J3. That's when you divide the 6 at angles by 6 at an angle 0 divided by 1 plus J1. This is an exact representation, and if you put it into a phasor form, it's like 4.242640687112 at an angle of negative 45 degrees. And so let's hold on to the precision while we can. So we'll break with convention for just a minute. Plus V2 over 1 minus J1 equals 2 at an angle of 0. Just for completeness sake and make sure that I don't screw up the math here, we have V2 over 1 plus J1 minus 3 plus J3 plus V2 over 1 minus J1 equals 2 at angle 0. I don't know that that was entirely necessary because we can, but we'll add 3 and subtract J3 from both sides. So that leaves us with V2 over 1 plus J1 plus V2 over 1 minus J1 equals 2 at an angle of 0. I guess plus 3 minus J3. Oh, so perhaps the easiest way to deal with this now is to pull out the V2, and the coefficients that were on the V2 were 1 over 1 plus J1, 1, and 1 minus J1 equals, let's see if this has a nice compact representation, 2 at an angle of 0 plus 3. Now the nice compact representation here is going to be 5 minus J3. So we'll leave it like that just for another minute. Divide both sides by all of this mess. Let's see if we can get this business in the parentheses into something a little nicer. So 1 over 1 plus J1 plus 1 plus 1 over 1 minus J1 is 2 at an angle of 0, or, yeah. So this is 2 at an angle of 0 times V2 equals 5 minus J3. And so if we divide both sides by 2 at an angle of 0, hopefully we still get the right answer. It works out, again, that V2 has a slightly more compact and perhaps exact form as 2.5 minus J1.5, but again, we by convention, we usually express it as a as a phasor, and that's going to be approximately 2.92 at an angle of negative 30.96 degrees. And at the end of the day, what we're really looking for is the current, but really the current I0 is V2 divided by 1 ohm. So it's not going to change the magnitude at all. It's just going to essentially change the unit. And you should get 2.92 at an angle of negative 30.96 degrees amps. Supernode goodness. So kind of keep that number around because we should keep getting that number as long as we keep doing this analysis. There's something pretty darn close to it. I'm going to go with the book here as we look at the nodal analysis or the mesh analysis, because the way that they've done it already deals with the need of dealing with some sort of super mesh kind of thing. And resistor and capacitor. Same circuit, negative J1 ohms here, 1 ohm, 1 ohm, current I0 that we're looking for, 6 at an angle of 0 degrees, 2 at an angle of 0 degrees, J1, 1. And so again, like I said, I'm going to follow the book and say, all right, well, we're going to make one of them nice and simple by having it hang around by that current source. We're also going to, part of the decision here to make this current I3 and to take I2 all the way around the outside, it does two things. One of it is a totally functional thing. We have, if we were to look at this, we say, well, there's 3 panes in the circuit. We're going to need 3 equations, but we would normally have this shared current source. So we already have to route one of the currents somewhere different, right? Either that or we have to deal with a super mesh. It doesn't really matter, but the upshot of doing this is that now I0 and I3 are essentially the same current. They're just going the opposite direction. So when we're solving for I3, or negative I3 equals I0. And so we have one less step to solve for, because we could have always taken I2 just and gone around this loop, but that would have made I0 equal I2 minus I3, and it would be just kind of one more step to do, one more way to screw up. But the other easy thing we can say is that I1 equals a negative 2 at an angle of 0 degrees amps, based on the way that we defined our currents. So, mesh analysis. So we can start writing our loop equations. At node 2, or at loop 2, we've got 1 times, this is the resistor, times I1 plus I2. We've got J1 times I1 plus I2. We run into the negative terminal of the 6-volt source. We run into this resistor, which is 1 ohm, times, here we've got I2 plus I3. And then we've got a negative J1 times I2 plus I3. And all that equals 0. That's going all the way around the outside of the loop. Going around the third loop, we've got 1 times I3. We've got 1 times I3 plus I2. And we've got negative J1 times I2 plus I3. And that equals 0. So we can try to simplify these things down, try to make them a little bit more reasonable to deal with. And I think what, well, let's go ahead and substitute in what we know about I1 to try to get this just down to the two unknowns. So we've got 1 times I1, which is going to be negative 2 at an angle of 0 plus I2 plus, let's see, how do I want to do this? J times I1 plus J times I2 minus 6 at an angle of 0 plus I2 plus I3, and I should have changed that one too. So the multiplying J times I1, which was a negative 2 at an angle of 0, that would give us, we can stick this in here as 2 at an angle of negative 90 degrees. So we'll stick that in next time we rewrite the equation. And then we've got a minus J times I1, 2, I2, and a minus J times I3, and that equals 0. So let's pull together the constants. We've got a negative 2 at an angle of 0, we've got a 2 at an angle of negative 90, and we've got a negative 6 at an angle of 0. So let's add those things up. Negative 2 at an angle of 0 plus 2 at an angle of negative 90 minus 6 at an angle of 0 degrees. And yeah. Again, my notes have it this way, and I'm going to, again, break with convention just for the more compact and exact representation. But when you combine all the constants together, what you get is negative 8 minus J2. So we will add that to both sides, and the right-hand side of the equation will become 8 plus J2. And that's what all the constants evaluate to. If you try to express that as a phasor, you get something that's very not compact, like 8.246 at an angle of negative 165.96 degrees, so not very kind of handy. So let's see, what do we have in terms of all of our other occurrence? We've got it seems like my notes are missing some of the complex stuff here, but so we've got, well, let's see. We've got a positive I2, and then we've got a JI2, but there's a negative JI2, so these should cancel out. And so we got another I2, and really that's all I see for I2 now is going to be 2I2. So we dealt with this one, we dealt with this one, we dealt with this one, this one, this one, this one, and then we're just left with I3 times 1 minus J. And that's our first loop equation, or simplified loop equation. Second loop equation to take a look at, or second one, which is for the loop at number 3. Try to simplify this out. We've got I3 plus I3 plus I2 minus JI2 minus JI3 equals 0. So I don't see anything that particularly cancels out here. We should just get 1 minus JI2 and 2 minus JI3. That's, yeah. So on the I2 term, we have 1 minus J1 times I2. And we've got on the I3 term 2 minus j 1, whatever, times I3 equals 0. And so here's our second equation. So those are our two loop equations. Exciting. And hopefully your calculator will also simultaneously solve things that has complex numbers in it. If my 10-year-old TI-86 can, I assume that your slightly newer calculator should be able to do it as well. But so the coefficient on I2 is 2, then the coefficient on I3 is 1 minus j1. Put that in there, minus 1. And that equals 8 plus j2. And the other equation is 1 minus j1, and then 2 minus j1. And that equals 0. You solve that. And we get, in rectangular form, we get both of these two currents as, so that's I2 is going to be 4.5 minus j1, and I3 equals negative 2.5 plus j1.5. So let's plug those in and just find out what those are as phasors. So that is, well, and yeah, let's just go ahead and do that. So 4.5 minus j1 as a phasor is 4.61 at an angle of negative 12.53 degrees. I3 negative 2.5, 1.5. Phasor 2.92 at an angle of 149.04 degrees. And what we had said originally was that negative I3 is the current that we're looking for, which is I0. So multiply that answer times negative 1, and you get, fortunately for us, 2.92 at an angle of negative 30.96 degrees. As you can see, the process is exactly the same. The math kind of sucks. You have to be so careful with the complex numbers that it's yeah. So it will take much longer than 4 minutes to do the Thevenin analysis on this. So we will go ahead and be done a couple minutes early here. What I will do is tomorrow we'll have a very simple quiz. I think what I will do is give you a network of inductors, capacitors, and resistors, a frequency, and ask you what the equivalent impedance is. So fairly straightforward, but enough to kind of get you to think about this AC stuff. Make sure you can do the stuff with your calculators. Turn in your homework number 4 if you have not already. And I will get solutions posted as quickly as I can. Enjoy your day, and we will see you tomorrow.